Today we have the pleasure to have here Jorge García Rojas. Jorge García Rojas is a researcher in the Instituto de Astrofísica de Canarias. He has a Severo Ochoa contract for 5 years now. Yeah, it's very good. Congratulations. And he also did his PhD research at the Instituto de Astrofísica de Andalucía under the supervision of Andalucía de Canarias and the supervision of César Esteban. That is a well-known people from many of us working in Orion. I am right?
Orion.
Yes. Okay, but Orion was your favorite topic, I remember. And then he moved to also with some good friends of us, like Manuel Peinber and Silvia Torres Peinber. And he worked in Mexico for 2 years and then came back to the IAC and he got a position at the observatory as super astronomer. And then recently, well, from 2014, he incorporated in the ISC as Severo Ochoa researcher. And today he's going to speak about supernova, and he will tell us the reason why he moved from Orion to supernova, to planetary nebulae. I'm sorry, but that should be some interesting question. Okay. Well.
I remember when I was doing my PhD in La Laguna, I was studying this thing, the abundance discrepancy in nature regions, in galactic nature regions, Orion, the Lagoon Nebula, etc., etc. And I was telling my supervisor, César Esteban, that I like very much planetary nebula. And he told me, oh, well, planetary nebula are interesting, but I'm going to recommend you to move to planetary nebula because each planetary nebula is different from the other. They are very complicated. H regions, you can study them as a whole, global properties, everything. Planetary nebula are much more difficult. Well, that is the main reason because I moved to planetary nebula, because it was a chance. So, well, I am studying right now with the collaboration of other people at the ISC and ISO and University College, the high abundance discrepancy phenomenon in planetary nebula. This is very interesting because we have found very recent results. We have found a link between this phenomena and other phenomena in planetary nebula. Well, this work has been done with very serious people, as you can see, mainly with Romano Corradi, which is right now the director of the UTC. Dave Jones is a postdoc at the ISC, but he's in La Palma working. Pablo Rodriguez Gil, who is our expert in binary systems, and Héctor Monteiro from Brazil, and Henri Boffin and Roger Wesson, which recently moved to the UCL, but he was in at ISO Santiago. I have to say that Roger Wesson is this one, not this one. Okay, this is a brief outline of my talk. I'm going to explain, to give a brief introduction to the abundance discrepancy problem, to describe some results in H2 regions, just to put everything in context. Then I'm going to move to the high abundance discrepancies in planetary nebula, and I'm going to talk about the binarity link, and then present my last results of about the location of the mission coming from recombination lines, and finally with the summary and future work. Well, recombination lines, metal recombination lines, metal, you know, in astrophysics metals, everything with more weight than helium, were first discovered by Weiss in more than 70 years ago. He found in this planetary nebula and in Orion, also in Orion, the carbon-2 recombination line and the oxygen-2 recombination lines. Since then, he realized that the abundance computed from these lines were very, very extremely high compared with the abundances computed from the classical collisional excited lines, the oxygen 3, 5007 line, etc. Well, since then, there have been a lot of studies, very deep studies in planetary nebula. These are some examples of very deep spectra in planetary nebula with a lot of detection of very faint lines. For instance, in 1995, Balotot et al. Of the group of Daniel Perignot detected more than 600 lines in NGC 7027, but with a relatively low resolution, so they cannot resolve very well the oxygen-2 recombination lines, which are in this wavelength range and which are in several planetary nebula, mostly in the most excited planetary nebula. There is a forest of permitted and also forbidden lines in this zone. So you need high resolution to blend these lines in the spectra. So with higher resolution, Sharpie et al. Found several lines a lot of lines in IC 4018. Also, well, different works by Sharpie, Painberg, the group by Xiaowei Liu, and by Barlow in the University College and in China. They made a lot of very deep study. Well, this is, probably you know him, is Xuan Fang. It was a postdoc here until 1 year or something like that. In fact, he made the deepest study of a planetary nebula in this object. He detected more than 1,200 lines in one planetary nebula, but with a relatively low resolution. 2 years ago, I made the study with the highest spectral resolution of this object, and you see 3918. I detect more than 750 lines, and also I detect. I had also kinematical information in the spectra because we have double peaked lines telling us information about the velocity field of the nebula. Well, this deep spectra is very interesting because we need a lot of resolution to the blend to compute properly the abundances from these recombination lines. What is the problem with these recombination lines? Because we wonder what is the origin of this abundance discrepancy. When we compute abundances always relative to hydrogen. When you measure lines of hydrogen in a spectra, hydrogen lines are always recombination lines. And the dependence of the emission of the typical recombination line, the H beta or H alpha, with temperature, the emissivity, the dependence of the emissivity is potential in this way. For the recombination lines, the metallic recombination lines, then the dependence with emissivity is very similar. It's very similar with the temperature. Emissivity, and this is the range of temperature typical of planetary nebula and its two regions. So the dependence is very similar. So if you have the ratio of both lines, you can compute abundances, and the dependence with temperature almost disappear. But if you use the collisional excited lines, this is the dependence of the emission of oxygen 3, which is talking about the same ion. Oxygen 2 recombination line is oxygen twice ionized, and this is oxygen 3 forbidden line is oxygen twice ionized also. The dependence is very, very, the dependence with the temperature is very important. These are different densities, log. So when you compute the ratio of this type of lines with respect to a recombination line, you have a strong dependence on the temperature of the gas. With the infrared line, the far infrared lines, the dependence is less important because you see the dependence in this range, the difference are much less important. This is because this term is very low, so the dependence is almost potential, not exponential, which is the important thing here. Take this into account, take this plot in mind for the whole talk, because this is important. You see the emissivity of the collisional excited lines at low temperature decrease a lot. But emissivity of recombination lines at lower temperatures increase. So take that into account for the rest of the talk. The point is that when you compute the abundances, always in almost all the objects, except one, probably I'm going to talk about that object later, you have that the recombination lines always give larger abundances than the collisional excited lines in all H2 regions and planetary nebula. And well, this is the abundance discrepancy dichotomy. And well, you have the ion, and depending what you are looking for, you see one C or another. This is a very nice picture made by a student. And then you can define abundance discrepancy factor as the ratio of both abundances. Abundances computed from recombination lines and abundances computed from collisional excited lines. This abundance discrepancy factor is most of the times larger than 1. And in several objects, in principle in H2 regions, this abundance discrepancy factor is more or less constant and about 2, 3 in most of the objects. But in planetary nebula, you have the bulk of the planetary nebula have an abundance discrepancy factor of about 2, 3, but you have an extended tail of objects with abundance discrepancy factors much larger, 20, 70 to 120. 120 is very extreme, and in two objects, which are going to talk, I'm going to go talk about them later, this ADF is extremely high, more than several hundreds. Well, what is the reason of this? There are several explanations for this. Temperature fluctuations proposed by Manuel Painberg. Also, there are other explanations that is chemically inhomogeneities, which is the thing that I'm going to focus in my talk, proposed by Silvia Torres Painberg, but developed in detail by Xiaowei Liu and collaborators. And also, well, the presence of a kappa distribution, a non-Maxwellian distribution of the thermal electrons, which was proposed by the group by Dopita, David Nichols and Mike Dopita. But in principle, this explanation is being put in doubt right now, because it seems that there is not really able to explain this abundance discrepancy factor. Well, I'm going to put my results in context with some results from 82 regions. As Pepa said, I work in Orion in several papers, and one of the papers in 2008, one of our former PhD students, Adal Mesa Delgado, made a long slit study in Orion. We put several long slits in Orion covering several morphological structures, different morphological structures. Protoplanetary disk, Herbigaro objects. We put also this slit position crossing the bar, the Orion bar. Well, we made this analysis and we found that in the Herbigaro objects we found very large densities, increases of densities in the Herbigaro objects, also in the Orion bar. We see also peaks of temperature, of electron temperature, in the Herbigaro objects and also in the Orion bar. And we also see here is the abundances computed from collisional satellite lines and recombination lines. These shadow regions, we could not detect the recombination lines, so they are shadow. And we found that in the zone of the Herbigaro objects, we found a peak in the abundance discrepancy. And the peak was mainly due to the decrease of the abundances obtained from collisional satellite lines, not from a increase of the emission of the recombination lines. It was from a decrease of the abundances computed from the collisional satellite lines. We speculate that maybe it was owing to shock heating. We made a detailed analysis of this Herbigaro object with a BLT using high resolution spectra, where we have in this Herbigaro 202, we have the slit position is this, and this is the Herbigaro object. We put the slit position in the bow shock, and we could blend both components, the high velocity flow and the normal gas emission, the background gas emission. Here in blue is the nebular component, the normal component, and in red is the shock, what we call the shock component. This is not strictly a shock, this is a photoionized shock. So we could treat this gas as a photoionized gas. And we found that from recombination lines, we compute almost the same abundance in the nebular component and in the shock component. But from collisional satellite lines, we found that the abundance obtained in the shock component was much lower than the abundance computed from the nebular component, and hence the abundance discrepancy was much larger. We are studying this phenomenon in other objects. We have a BLT spectra of all these objects, and this is a project that is right now going on. But what we found is that the ADF was related to the presence of this high velocity flow. On the other hand, we also study, in collaboration with Yanis Samis, some works by Yanis Samis and some work made by Adal Mesa Delgado, with 2D spectroscopy using flames and using PIMAs, we found that the presence of high density clumps, extremely high density clumps, like the proplyds are, the protoplanetary disk in Orion, we found that these high densities modify significantly the chemical abundances obtained from collisionary satellite lines, but not the abundances obtained from recombination lines. And what we did was to study the emission from trying to isolate the emission coming from the proplyid. When you compute the density, for instance, in a proplyid, this is a protoplanetary disk. When you compute the density, you are considering the gas coming from the protoplanetary disk and the gas coming from the nebula in front of the protoplanetary disk and back to the protoplanetary disk. So you are summing with different weights the different densities. But the problem is that the protoplanetary disks have extremely high densities of the order of 1 million particles per cubic centimeter. So if you do not consider the right physical conditions when you compute the abundances, you are probably computing a bad density, then you are probably computing a bad temperature, and then you are probably compute a very bad abundance. So if you isolate the protoplanetary disk, what we found is isolating the protoplanetary disk and considering the right density, you have a lot of influence of the collisional desexcitation in the intensity of collisional satellite lines. So using the appropriate diagnostics, for instance, computing densities not from the usual diagnostics like sulfur 2 lines or oxygen 2 lines or even chlorine 3 lines, but using iron lines, which are very sensitive to these densities, this range of densities, and making a proper selection of the background around the protoplanetary disk, we found that the ADF, the abundance discrepancy factor, comes when to 0. So we finally found the abundance from the combination lines or for collisionary satellite lines being the same. So probably high density clumps have influence, the presence of high density clumps have influence on the ADF in H regions.
Jorge, how do you actually isolate the clumps from the background, foreground stuff?
In the 3D spectra, I don't know exactly the technique because it was done in this paper by Yannis Samis. This paper was done by Adán Mesa Delgado. He made, I don't remember, these regions at the typical, he made an average of the emission of the nebular component, and then he subtract from the emission of the protoplanetary disk. Huh?
The contribution is significant.
Yes. Yes, because here you have, I think this is the observer, this is the black one, the background is the blue one, and the isolated protoplanetary disk emission is this one. But the interesting thing is that Yannis Samis in his 2 papers and we in our paper found the same. We found the same. We found that the ADF disappears if we isolate the emission of the proplyid. Well, I'm going to planetary nebulae. I'm going to. This was a very large introduction of the problem. In planetary nebula, where you have these 2 objects, which are Abel 30 and Abel 58, where Roger Wilson found the larger ADF in planetary nebula. This is in the nodes of Abel 30. These are H-poor nodes. These are in principle a planetary nebula that is called a born-again planetary nebula. In principle, this planetary nebula is thought to have experienced a very late thermal pulse. So eventually there was an ejection of H-poor material, and this H-poor material, if you compute abundances, you have a very large abundances from the combination lines, not because you have a lot of oxygen from the combination line, but because you have a very low amount of hydrogen. So the ratio increase a lot the abundances. Also in abril 58, in this node, they found very large abundance discrepancy factors. The problem is that if you try to explain this with a very large, very late thermal pulse, you expect that the carbon over oxygen ratio in the ejection should be carbon rich. But in fact, what you found in this spectra is that the ejection from the combination lines, the carbon over oxygen is less than 1, so it's oxygen rich. So the very late thermal pulse to explain this behavior is not, cannot explain it very well. But on the other hand, Roger Wesson also proposed that maybe you can have a binary system in the central star of this planetary nebula, which are not confirmed right now, and maybe it was these ejections were owing to a nova-like ejection, because they found that the chemical pattern of the gas was consistent with a nova-like ejection. The problem was that the rising brightness of this, the central star of this planetary nebula, is not consistent with the time scales what you expect in a nova-like explosion. So, well, also Lau et al. Proposed a combination of very late thermal pulse and nova ejection to explain abril 58 nodes. I'm not going to enter in detail in this. But when we measure the ADF in a planetary nebula, not concentrating in a node, but including most of the planetary nebula or a large part of the planetary nebula in our slit, we usually found normal ADF, but Liu in this object HF22 found an ADF of almost 70, and he realized that the central star was a closed binary system, a post-common envelope binary system. And this was the first speculation about a possible link between the binarity and large ADF. They also estimate the ionized mass, because it's an estimation, because you need the distance to the nebula, and the distance to the nebula right now, you know, until Gaia in 2 years, or 1 year or 2 years, gave us reliable distance. They estimate that the ionized mass was very low, extremely low to be a planetary nebula. They think that this nebula was mainly a common envelope, post-common envelope nebula. Okay. Well, this is a brief explanation of, for those of you who don't know which is a common envelope phase. It's a very short phase in the life of binary systems. The primary, in which the primary stars evolves, increase size, fills its log Roche, then there is a overflow of Roche log, and start the mass transfer. The secondary cannot account for such amount of mass, and also fills its Roche log, and they found a common envelope. So that they have a common envelope inside, and the orbits get closer owing to drag forces, and the loss of orbital energy produce the heating up and the ejection of the envelope. And then, well, the envelope is eventually expelled into space, and you finally have a very close binary system with periods of the order of days or less, 1 day or less, even less, and you have a small nebula, very faint and a small nebula. Well, we decided to study this because since 2006, when Mo and Ursula de Marco suggested that a large proportion of planetary nebula have binary stars, binary central stars. In the last years, there is an increasing number of systems detected, confirmed as binary. There are some of them even proposed as triple systems. But, well, you can check the whole list in the Dave Jones webpage, in drdjones.net. There is a complete list of these systems. And what we found in 3 years ago was that in a paper led by Romano Corradi, he was studying the central star of this planetary nebula. It was a IFAS new discovered planetary nebula called O5, and he found that the central star has a sinusoidal modulation, clear sinusoidal modulation, and well, it was a clear binary system with a very clear, very close, very small period. And looking at the spectra of the nebula, they took 2 positions, but looking at the spectra of the nebula, they found that there were 2 very high emissions, which we identified as the carbon-2 and a blend of several oxygen-2 lines. That's why we need high resolution, because here with this resolution we would not resolve the oxygen lines. These are some features encourage us to request time to the William Herschel telescope for this planetary nebula, another planetary nebula with known central binary stars, Abel 46 and Abel 63. We took very, very deep spectra of this planetary nebula. We spent more than 2 hours on target on each of them. And with the help of PyNet, which is a software developed at the IAC and the Instituto Astronomía of UNAM, we compute everything, the physical conditions, the chemical abundances from both chemical collision excited lines and recombination lines. And what we found was that you can see here the strong carbon-2 emission and oxygen-2 emission is very strong for the usual thing. And we found that extremely high ADF. In Abel 46, it was the largest ADF, the highest ADF found for a whole planetary nebula, more than 100. And for O5 it was also extremely high. For Abel 63 it was larger than the usual ADF.
So these are integrated spectra? Integrated?
These are spectra integrated in these slits. It's not the whole nebula, but it's a significant amount of the nebula, crossing the central part of the nebula. For integrate the whole spectrum of the planetary nebula means that you have to scan the nebula. When you scan the nebula, the resolution is probably not enough to blend very good, to have a good blending of the oxygen 2 recombination lines. So what we found also was from cuts in the profile of the emission. We found that these were the cut of the emission along the slit of typical helium and hydrogen recombination lines, and these were the cut of the emission of collisional excited lines in the nebular emission of a collisional excited lines and the auroral emission of a collisional excited lines. This is the line that the ratio of these lines is used to compute the electronic temperature. When you see that the profiles are different, you know that there are probably a temperature gradient inside the nebula. But the important thing is that the emission from the recombination lines were very different from the emission of the hydrogen and helium recombination lines, and also very different from the emission of the nebular collisional excited lines, but similar to the emission of the auroral collisional excited lines. We still don't know what that means exactly. We still don't know. But the thing is that the recombination lines emission were concentrated in the central part of the nebula. Also, we compute the nebular estimate, the nebular ionized hydrogen masses in all the objects, and we found that they were too low to be planetary nebula. So probably we speculate with the possibility that they were the result of a common envelope ejection. Also in this object, NEC 6778, also with a close binary central star, we found the same behavior. We found that the collisionally excited lines profiles were very different from the recombination lines profile. Here you see the collisionally excited lines are this blue, the oxygen 3, and the recombination line and auroral line profile of oxygen are these two. So these profiles translate in an ADF that increase to in the central parts of the nebula. This planetary nebula has also a central binary central star, so we strengthen the link with it. We decided to take advantage of the tunable filters in the GTC to try to make the first image, direct image of the recombination line emission ever in a planetary nebula, and we got this image. Well, this spot here is the central star, but we got that the emission of coming from the recombination line, this is the tunable filter width in this recombination line, that the emission coming from this recombination line was concentrated in the central part, and it was the structure, it was very different to the emission coming from the collisional excited lines, the nebular collisional excited line. So we have this behavior, the emission of the collisional excited lines in the outer parts and the emission from the recombination lines in the inner parts.
Okay.
Yes.
Why the central star is so bright in the oxygen 2 image? Much brighter than in the oxygen 2.
Probably this is a combination that this is central star and emission, and but
But this is also the same in the OCN3 image, or is there any continuous abstraction? Or
No, there was a continuous abstraction.
that was not?
There was. Here.
Okay. But not in the OCN3?
No,
Okay.
no, because we need a lot. We would need a lot of time to have a continuous subtraction. We have a sky subtraction, but continuum.
So this is not real OCN2 emission from the central star?
This not real oxygen emission from the central star. It's continuum. This is the continuum. But here you don't have continuum emission almost. We did the same for abril 46. It was much more difficult because it's much fainter. We have here the same problem. We have the central star, well, a lot of continuum emission, but we found that the emission of the recombination line, continuum plus recombination line, is concentrated in the central part, just in the parts where the emission of the nebular line is lower. So this is a common effect found in several planetary nebula, where independent of if you have a closed binary system or not, several authors have found that the ADF peaks in the central parts of planetary nebula. For instance, Liu et al. Found for NGC 6153 that the ADF peaks in the central part of the planetary nebula. Harriet, Donald Garnett and Harriet Dinenser also found this in the Ring Nebula, from this spectroscopy study of the Ring Nebula. They found a small peak of the recombination line emission in the central part. These are long slit measurements, so they measure the line, so you have no continuum here. Well, but it seems that this phenomena is increased in this high ADF planetary nebula. We also found this thing with a very extreme ADF in N142. N142 is a planetary nebula with a large ADF, a high ADF, but not known central binarity of the central star. But well, we suspect that probably, taking into account all the things we have found, probably is a candidate to harbor a closed binary central star. But maybe it cannot be detected right now. We are doing a campaign trying to doing radial velocity studies, trying to see if this central star can be a binary, closed binary central star, because we found a very extreme ADF in the central part, more than 100, almost 140. So, well, it seems that maybe it's a candidate. What we also have found is that with Muse data, these are preliminary results. The continuous subtraction of this data is not easy. But in principle, these two objects have relatively low continuum emission, and we could see that the emission coming from the recombination lines, the fainter line, is concentrated in the central part. It's the same result that we have in this object with the tunable filters, and in this object is new results. This cross represents spaxel, just to see you the apparent different location of the emissions. We want to do a detailed analysis of this Muse data to constrain with the detailed B abundance photoionization models. Saying photoionization models considering two different chemical components. One component with H-rich normal abundances, and the other component with H-poor oxygen, carbon, and neon and other elements enriched. The bad thing here is that we don't have, in the MUSE data, we don't have the information of on the auroral line of oxygen. So we don't have a good constraint. Wait, sorry, I don't know what happened. A good constraint for the temperature. Let's see. But we have, with the MUSE data, we have a constraint for the nitrogen 2 temperature. So, well, we have to work with that. We are obtaining also time in different telescopes around the world with 2D spectrograph, trying to cover the auroral line, the recombination lines, and the nebular lines in one shot, just to add additional constraints to the photoionization models. Well, let's see. Well, this is the distribution of the ADF measured in all the objects along the history of the ADF measurements. And we have the medium, the red is the median, and this is the 80th percentile. The red objects are H2 regions. The green ones are typical planetary nebula, and the blue ones are planetary nebula with close binary central stars. It is clear that they are concentrated in the high ADF range. This is an outlier, a clear outlier. It was NGC 5189. We thought in principle that it was a problem because the slit with this measurement was only covered a very small part of the nebula. But we are realizing right now with additional observation that this is real. This planetary nebula has a close binary central star and a low ADF. There is the photoionization models we plan to do with to constrain the MUSE data are typically similar to these models made by Yuan et al. Using the moccasin code, which you have a H-rich component with these abundances and a H-poor component. The H-poor, they put several droplets of small droplets of gas inside the normal gas composition, but we plan to include a component not in droplets, but maybe a component concentrated in the central parts of the nebula with this different composition. This composition is of course much less massive than the typical H-rich component, colder, much colder, because there is an increase of recombination line emission, much denser, and the relative abundances with respect to the H-rich component, well, much higher than the normal composition. With this, you can, for instance, Haibo Yuan and collaborators reasonably reproduce the spectra, the observed spectra of NGC 6153. Reasonably, not all the things, of course, because they had problems with the reproduction of reproducing the infrared emission of this object. Well, we are collecting new data. Well, we are finishing the analysis of new data. Several post-common envelope close binary central star planetary nebula, where we have found we have measured the ADF, and in all of them we have found very large, very high ADF. This is a work led by Roger Wesson. These new objects are these dark blue objects, also concentrated in that part. We have found also in a paper that is in preparation, well, not in preparation, it's submitted, sorry. The Sowika et al. Is a student, a master student. She was analyzing, the kinematics of this Wolf-Rayet planetary nebula with a central binary star, but with an intermediate period. The central star have an intermediate period with this, from several to few tens of days. It's not very close, it's intermediate, and it's similar to NGC 5189, which has also an intermediate period. It's only the period, it was thought that it was close, because it was only a few days, but we found that they have in common that the period is not so small. It's not as small as the period needed of the period the high IDF planetary nebula have. So these two objects have binary central stars and low ADF, quite low ADF. So probably there is a limit in the period. There is a limit where the physical processes produce some kind of nova-like ejection or something like that, and increase the ADF you measure in the gas. Well, but that's not all, because in a very recent paper, Mike Richer have found that the central concentration of the emission of recombination lines is a common thing in planetary nebula. He analyzed the emission, he did a kinematic analysis of the emission of the carbon-2 6578 Armstrong recombination line, which is a recombination line that is sometimes is affected from starlight excitation. But they did a very careful work. They modeled with different central star Thomas Rauch models with cloudy. They modeled the nebula. They compute the fluorescence contribution of the line at different for different central star temperature. The red emission is the carbon-2 emission, normal recombination emission, and this line is the fluorescence emission, which is a small contribution relatively to the other contribution. And they found that the expected location in ionization equilibrium of the recombination line emission did not fit what they observed. They observed this is the expansion velocity, I thought. Yes, with respect to H alpha. No, this is the width of the line with respect to H alpha, and they found that the carbon-2 lines, in principle, were located in the central, more centrally located than the emission from oxygen-3, and that's what's is not expected from the oxygen-3 is the blue. This is the carbon-2. That's not expected from the ionization equilibrium. So probably they argued that this was a reason to expect that there were several components. This is ionization equilibrium of only one emission component. So they speculate that it was a reason to think that there were several emission components. Finally, for the future, we plan to use Megara, which is right now the commissioning starts in 1-2 months in the GTC, to map the spatial distribution of recombination lines and collision accepted lines, and also to study the kinematics of the gas coming from the recombination lines and coming from the collision accepted lines, just to try to resolve the puzzle we have with this emission. Also, for the future, We also think with that harmony using the B plus R disperser at much lower resolution. It would be nice to study the recombination line distribution, spatial distribution in a lot of planetary nebula with very faint emission from the combination lines. So we need a very large telescope. So to finish, this is the summary and the future work. We predict that many of the planetary nebulae with large abundance discrepancy factors are post-common envelope closed binaries. We have a lot of several candidates for binarity because we found large ADF, but we don't have information about the central star. We are collecting data. We are checking deep spectra of other planetary nebula with confirmed post-common envelope central binary star. The paper is in preparation, and in principle in 1-2 months is going to be ready. We found from direct imaging with tunnel filters that the spatial, and also with Muse data, we found that the spatial distribution of the recombination line emission is concentrated in the central parts of high ADF planetary nebula, and is clearly concentrated. The higher spatial and spectral 2D spectroscopy will shed more light in the end of the recombination line emission and in the link of the ADF with the binarity of the central star. This is very interesting that we find that the planetary nebula with intermediate period post-common envelope binary central star do not show high ADF, so there is probably a physical limit in the binary system to eject this H-poor or metal-rich material. The important thing and the message to take away is whatever the origin of the high ADF, not all the ADF, the high ADF seems to be related with the evolution of close binary central stars. But this is not a solution for the ADF problem, because in H2 regions you still have this problem. There are several possible origins that I explained at the beginning of my talk, and probably in the bulk of planetary nebula there are other physical reasons related to this or not, who knows. But the point is that explanation as temperature fluctuations or kappa distributions cannot solve for sure the high ADF behavior. And you need the two chemical components behavior to explain this high ADF. The problem is what is the origin of the two chemical, and what is clear is that it's related with the evolution of this close binary central star. So I finish here. Thank you.
Thank you, Jorge, for this very interesting and nice talk. Is there any question?
Jorge, thanks a lot for your talk. One question which is not completely related to the abundances discrepancy, but that you have mentioned here, as for the born-again planetary nebulae, we know that the carbon to oxygen ratios are not what we expect from the very late thermal pools. In particular, oxygen is much abundant than we were expecting. You know that those sources, they form in a very short time scale a lot of dust, and this dust can trap a lot of carbon atoms. Is Wesson taking into account those effects when computing the carbon to oxygen ratios?
No, I think he did not compute that. And in fact, what I understand is that carbon can be trapped by the dust of oxygen also. And the relative amount of dust depletion of carbon and oxygen, at least from my knowledge, in H2 regions is similar. In planetary nebula, I'm not sure. I'm not sure because, well, there's another problem related to that, but that is interesting. Gloria Delgado Inglada and collaborators found that there were overproduction of oxygen in carbon-rich dust planetary nebula. I'm not sure if this can happen in this scenario.
Just to mention here that the dust production in those sources is so fast. I mean, this is not the typical dust production. It's a process which is probably not well understood. So maybe the carbon to oxygen ratio trapped on those dust grains is not what we are used to find.
In his papers, I think that Roger did not consider that. He computed the carbon over oxygen ratios directly from the gas, the ionized gas. But taking into account that Roger is working a lot on dust production in supernova and everything, probably in future analysis he's going to explore this. Yes, maybe it's a solution on this issue.
Any further question?
Just a few comments to this very interesting work, because we look at the images and they seem like images from emission lines, so we know how to do that. But these are very, very faint emission lines, so this is very difficult, very detailed work that your group is doing for the last few years, which is very exciting, very interesting, and I congratulate you for this. In particular, 2 or 3 particular points. With respect to the continuum image from the GTC, the oxygen 2 image from the GTC, I think this continuous subtraction is important. You mentioned that it's difficult, that you haven't done it, but you have the nebular continuum underlying there. And
that's why we decided to do Muse observations.
Muse
yeah,
is reliable.
because
result, Muse is completely reliable, yes.
For sure, that's important. Well, in principle, we published this paper as the first image, but the continuum, it was impossible in the proposal. We argued that we could not obtain a continuum. Well, we are.
But you didn't have the
H alpha line? Do you have an image in H alpha or H beta?
In this,
the GTC.
no.
No, okay.
No.
So it's not possible then, okay.
Only in we took 5 hours or something like that. A lot of time to obtain this image.
As you mentioned, you're not providing, and it's still far from clear what is producing this high abundance. The ADF, sorry, the high abundance is one explanation. As you mentioned, it may not apply to H2 regions, for example. Maybe the physics is different there for the ADFs. I wanted to ask you, but you already answered it. I had the question before you answered it. Whether anyone, other groups, or you are exploring different physics, like the one that you mentioned of continuum stellar excited fluorescence. because if it is concentrated in the inner parts, it's also maybe pointing to some or other physical effects apart from fluorescence.
It was
just before.
The recombination lights that you're using, they're not affected by fluorescence, at least that it is known, as the one that the carbon 2 that you mentioned later from this other work. The other lights that you use, the oxygen 2 and the other carbon 2 lines that you use, are they affected by fluorescence or they're not?
4267, for sure not, because it's a 3D 4F transition. That's impossible to excite with fluorescence. The oxygen 2 multiplet 1, which is these oxygen 2 lines around here, there are some models that Vladimir Escalante and Christophe Morisset made for IC 418 and for the Orion Nebula, where they say that there might be some small 20% or something like that, small contribution of fluorescence, of starlight excitation. They made that, well, you know that in they made photoionization models. They use a very detailed description of the ionizing source, because you need that to study the fluorescence. And they had a very detailed model of the central star of IC 418. And I think they use also information by Sergio Simon Diaz et al. On the ionization sources in Orion of the trapezium stars, and they found that. But they are low ionization objects. So maybe in low ionization objects you have more the influence of, let's show you, with maybe the influence of fluorescence is important in objects excited with a lower temperature star, so they have low ionization. But in higher ionization objects, the influence of fluorescence in general is much lower. So for sure, probably there is some influence of fluorescence in some in these oxygen 2 lines, but mainly in low ionization objects, and this can only explain a low amount of the observed ADF. That's one of the reasons that I suspect that there are several things contributing to the ADF. Another one thing is the possible, in the binary central stars, you know that if you have a very closed system, there is one of the stars, one of the side of one star is irradiated. The colder star is irradiated by the hotter star, and there is some emission coming from that. I don't know if there is in the Eta Carina, in the Eta Carina system, that there is some nitrogen and carbon emission, strong nitrogen and carbon emission in the zone where the multiplet 1 of oxygen is found. I did not check that, but maybe some part of the oxygen emission is also owing to this irradiated emission. I'm not sure at all. This is a thing that I want to investigate. But well, for sure, probably the planetary nebula complicated objects, they have, as I was talking with Martin before, they have shocks, they have also, probably several planetary nebula have high density clamps, and maybe all these things are contributing in a different manner to the global ADF. So,
are you using the sulfur 3 lines to compute the electron temperature with the Muse data?
The sulfur 3. Well, we can compute the temperature with sulfur 3 lines, but I didn't analyze still this part. I am concentrated in isolating the emission, subtracting the continuum in the recombination lines. The analysis, the whole analysis is, I'm going to start in 1 month or something like that. But of course, I'm going to use the sulfur 3 instead of the oxygen 3, because we don't have this auroral line of oxygen 3.
Okay, thank you, Jorge, for this nice talk and the debate.